So today we are here to attend the talk by Professor Patricia Lustosa from Catholic University of Rio de Janeiro, talking about symmetric and asymmetric superlattice quantum well infrared photodetectors. So Patricia Lustosa de Souza received the bachelor and master's and doctorate degree in physics from the University of California, San Diego in 81, from the San Diego State University in 84, and from the Catholic University of Rio de Janeiro in 89, respectively. In 89, she joined the Catholic University of Rio as assistant professor, where she is now full professor and head of the semiconductor labs. She is also head of the National Science and Technology Institute on Semiconductor Nano Devices, DISI. She has been engaged in research in 5 semiconductor materials for electronic and optoelectronic device. She is since 2006 an Olga Tauski Fellow from the Wolfgang Pauli Institute. So, and Patricia Lustosa is also the general chair of PUC-Rio next year. So if you want to meet Patricia in person, prepare nice papers for the conference next year. Soon you are going to see the announcements, and I think everybody will be happy to go to the conference in person again. And as you know, Rio is a wonderful location, and Patricia is a wonderful general chair. So be prepared to submit nice papers for this special edition, where we are going to return to in-person chip-in series of conference. So, Patricia, thank you again for accepting our invitation to give the talk today. So the floor is with you to start your presentation.
Well, I'd like to start by thanking Ricardo Reis for this invitation. It's really an honor for me to participate in this series of very nice seminars. And also, I would like to thank you for the nice introduction. So with that, I will start to talk about symmetric and asymmetric superlattice quantum well infrared photodetectors. This is a work that I've been, let's say, working on this subject for many years now. And obviously this work has been, I have many students, postdoc, and other professors, collaborators working on this subject. So this is what I'm going to show you is the result of joint research with all these people that are listed here, who belong to different institutions, as you can see, from my university, the Catholic University, the Federal University in Rio, and also from Unicamp in Brazil, and also a collaboration with Princeton University in the US. So to start, I'm going to talk about briefly the motivation to work in mid-infrared photodetection. And what I mean by mid-infrared, I'm talking more or less between 2 and 20 microns. And there are many areas of interest for this photodetection in this wavelength range. So one of them is the free space communication. It can be between satellites or between buildings, because, for instance, the window of 10 microns is where you have the smallest absorption due to rain or clouds. So this is really the best window for free space communication. Also, another area of interest is the industrial inspection, where you can have, we have many molecules that have absorption in this mid-infrared range. Here I have a few of them shown in this graph on the bottom left side. So one can use these infrared photodetectors to detect leaks, for instance, in industrial systems. Additionally, in one area that is of major interest is the thermal imaging, that you make an image where you can detect the black body radiation, or the radiation that every object emits at certain temperatures. And for instance, room temperature 300 K, it's around 10 microns also. So this is a good wavelength for thermal imaging. And obviously, the infrared detection has major applications also in the military. So, I mean, but it's a dual application. I mean, you have civil and military applications. And one of the reasons actually we chose to work on this field is because given that it has many applications in the military, it's very, it's an strategic. I mean, it's important that we can have the technology of infrared photodetection, because it's many times, it's very difficult to buy infrared photodetectors, even for civil applications in the market, because of the military applications, exactly. So it is, to some extent, strategic. Well, in the past, yes, I'm having a difficult, okay. The technology that has been mostly used in the past years for the infrared photodetection is the technology based in MCT. This is the material, which is an alloy of mercurium cadmium telluride. So MCT, mercuricadmium, that's how people normally call it. So the MCTs, they are the semiconductor, and it's based on a interband transition. So you have photons that are instant and are absorbed by electrons in the valence band of the material, and then they promote the electron to the conduction band. You apply potential, and then you have a current that is generated, which is proportional to the intensity of the optical signal. This alloy, the importance of this alloy is that you can tune the band gap, and therefore the detection wavelengths. You can have the mercury telluride. So if you have 100% mercurium in the material, then the gap is essentially zero. So you can go from a zero band gap to the visible, which the cadmium telluride has a gap in the visible. So you can tune, by changing the composition of this alloy, you can tune the whole mid-infrared range. So this is a very good thing, but it has disadvantages. And the major disadvantage with this material is that you cannot make it homogeneous enough in a large area. So if you want to make an image, a thermal image, you need to have a matrix with detector. Each pixel will be one detector. And all these pixels, they have to have exactly the same performance so that they can make an image that is a true image of a scene. So for that, you need a material that is homogeneous in a large area. And this is not the case with this material. And for telecommunications, for instance, the free space communication, its material is relatively slow for that. And the yield in a factory is relatively low because they are mechanically fragile. So, I mean, the yield in a factory is not so nice. So the idea is to turn into a material that has more mature, technology that's more mature, that you can have a homogeneous over a large area. And this would be the 3-5 semiconductor. So alloys based on indium phosphide, gallium arsenide, and so forth. It's still based on the band-to-band absorption, same type of the mechanism of current generation is exactly the same. But the problem is that, contrary to the MCTs, one cannot tune the entire mid-infrared range. So in fact, for longer than 1.7 microns, it's very difficult to have good quality material. So the idea is, if you want to use this material that has a very nice quality, you have to change the technology, the mechanism of current generation. And the idea here is to use quantum wells. So if we use quantum wells, as shown in this graph here on the right side, you can dope this material so that you have levels that are discrete, quantized energy levels. And then if they are doped, you dope so that the fundamental energy states is populated. Then you can have photons that are incident with the energy that coincides with the difference, either goes from one bound state to another bound state, or it can go to the continuous, and then you can generate a current. And then by changing the thickness of the quantum well, one can tune the absorption wavelength. So this is the idea. And these materials, because you have transitions between bound states, they are more selective, but they have one big disadvantage. The disadvantage is that they don't absorb light that is incident perpendicular to the material, which is in most cases, that's what you want. And the reason is because for that transition, this what we call intersubband transition between bound states, for it to occur, we need a component of the electric field perpendicular to the layers. And then to have the incident light, the electric field is on the plane of the layers. So you have to make the light incident with an angle, which you will lose part of the signal, or you need to introduce a diffraction grating so that you can generate a component of the electric field perpendicular to the layers. So this will be shown in the other slides. So here shows, I mean, the black lines are let's say, the spectrum, the absorption spectrum of different bulk material. And for the quantum well, we can see that it's very selective. So we have this QWIP here in blue. And as for the fact that normal incident light is not absorbed, as I said, either we make the light incident with an angle, as shown in the top figures here, or we introduce this diffraction grating that will generate the component. So this is how they work now, these QWIPs, and that will be the major subject I'll be talking about in a minute. Before I can tell that there is another family of detectors, which are the quantum dot infrared photodetectors, as opposed to the QWIPs, quantum well infrared photodetectors, which are also based on the intersubband transition. And because of this three-dimensional confinement, in the case of the quantum dots, the confinement is not just in one direction, but in three directions. This selection rule of the component of the electric field perpendicular to the layer is abolished. So with the quantum dots, one can have absorption of the normal incident light. So this is a big advantage as opposed to the QWIPs. However, obviously for the quantum dots, the volume of the dots, I mean the volume of the material, is smaller than with quantum wells, obviously, and the homogeneity is not as good and very low, poor reproducibility. So these are disadvantages. So I will be talking about QWIPs. And as I mentioned, the QWIP, the quantum well infrared photodetector, they are based on the intersubband transitions. And then we can have two different geometries, let's say. we can have a transition between a bound state, let's say the ground state, and the continuum. And then since the electron goes to the continuum, it's very easy to generate a current. The electrons are already free. You just put an electric field and that's it. The current is generated, very easy. Or if it is a bound-to-bound as shown here in this graph, we need a mechanism to extract the excited electron so that it can generate a photocurrent. And there are ways of doing this. One is you can make the barriers thin enough, and then you can, for instance, rely on the tunneling through the barrier as shown here on the right side. So this is one of the mechanisms that is possible. So we have decided to face, using these QWIPs, using this technology, to face two challenges in the infrared photodetection for the 3.5 material. And one is what we call the detection within the forbidden gap. So as I mentioned before, band-to-band transitions, one can only have, we can only obtain for wavelengths that are shorter than 1.7 microns, because this is the limit of the band gap of the 3.5 materials of good quality. And I will go back to this previous slide. If you can see here on the figure on the left side, the transitions, the energy that we can absorb, and therefore the wavelengths, is limited by the band offset, meaning the difference in energy between the bottom of the conduction band of the quantum well and of the barrier. So this is the maximum energy that can be detected, or minimum wavelength. So then I go back to the slide. So it means that because we are limited by the band offset, so we cannot detect wavelengths that are longer than 2.5 microns, or meaning energies that are larger than, let's say, 500 milli-electron volts, more or less. So there is a gap between 1.7 microns and 2.5 microns. That's called forbidden gap for the 3.5s, in which is a range that is very important. For instance, is the best range for environmental monitoring, for instance, for imaging. So it is an important wavelength range to be reached. And to face this challenge, we have used symmetrical superlattices, as I'm going to show, with a structural defect. And this I will get into more detail in the next slides. And the second challenge is the detection at room temperature, because these detectors, since we are detecting energies that are very small, we are talking about 500, 600, 300 milli-electron volts. So normally you need to operate them at very low temperatures, because just the thermal excitation is of the same order of magnitude as the signal that you want to detect. So this is a problem. I mean, detection at room temperature for the mid-infrared detection is like the Saint Grail of the infrared photodetection. And for that, we use the asymmetric superlattice with a structural defect. And I will explain exactly what those two types of structures mean. Okay, so let's get into business now. I will skip this because this I already explained. So here are the type of structures that I'm talking about, the superlattices with a structural defect. So what is this? So I have a superlattice, meaning quantum wells with thin barriers, so that let's say the quantum wells, they can feel the presence. Oops, sorry, I went back. Can feel the presence of the one next to it. So, I mean, we have wave functions that are a combination of the wave functions of all these quantum wells. I mean, they feel the presence of the one next to them because the barriers are thin enough. So here I have this periodic structure, And I will put a structural defect, meaning I will introduce one quantum well that has a different thickness from the other periodic, the otherwise periodic structure. So here the central quantum well is larger than the other ones. So this is what I call a symmetric superlattice with a structural defect. So what happens is that a superlattice with a structural defect gives rise to localized states, not only in the bound area, I mean, in energies that are below the bottom of the conduction band of the barrier material, but also in the continuum. So in the continuum, I will have localized states. So this increases exactly my tunability. I'm not limited by the bandoffset anymore. And since it is in the continuum, it is easy to extract these carriers. The idea that this type of structure give rise to localized states in the continuum, this was first shown by Capasso in 92. This idea was used by Leavitt to make one infrared photodetector. However, they did not use it to reach wavelengths that were unreachable otherwise. They used to reach wavelengths that QWIPs could already reach. So, and that therefore, so we used this idea to reach forbidden energies. So going to the next slide. So the idea here is that we have used, so first doing some design and theoretical calculations for this type of structure. We use indium gallium arsenide as the quantum well, indium aluminum arsenide as the barrier, lattice matched to indium phosphide. So it's more or less, they have half indium, more or less 50% indium, 50% gallium, and 50% indium, 50% aluminum. And in this figure, the one to the left, we see the structure of the quantum wells, of the superlattice structure with the structural defect in the middle. So the dimensions, just for you to know, the central quantum well is 7 nanometers. The lateral quantum wells are 1.5 nanometers, and the barrier 3 nanometers. And what you see, these lines in blue and green, is the probability density for the different states. And in gray is the mini bands that are generated by the superlattice. So the localized state, the first one, the ground state, is here in blue. Then we have in green the first excited state. The second excited state is already in the continuum, as you can see here. And the third excited state in green in the continuum. As you can see, the first state, if we have a symmetric structure, we have an alternation between states that have even parity and odd parity. So the first, the ground state, is even parity. Then the second one is even, odd, even, odd, even, odd, and so forth. And in these structures, there's a selection rule that I can only have optical transitions if I have a variation of parity, meaning I can only have absorption going from an even to an odd parity state. So I can only have transitions from the ground state to the first excited state, or from the ground state to the top level there, the third excited state. From the first excited state to the, I want to go back. From the first excited state to the second excited state is forbidden. In the figure to the right, this is the result of the calculations of the probability of the absorption, in fact. So as you can see, we have the highest probability of the transition between the ground state and the first excited state. That is 190 milli-electron volts, corresponding to about 6.5 microns, the wavelength. And then we can see, I forgot to say this. The line in the graph in the right figure, in blue are the transitions that start in the ground state. And in green, the transitions is starting in the first excited state. So it's starting in the ground state. I can only have transitions to the first excited state, as you can see, very strong. And then I have, these oscillations here in blue means these are transitions to the mini band states. And then we don't have absorption to the second, as I said, this is forbidden. And then we have the absorption to the third excited state. And if we see the difference in energy is 621 millielectron volts above the bandoffset, 2 microns within the forbidden gap. So this is what we want to reach. The bad news about this, as you can see, this absorption is an arbitrary unit, but it's in the log scale. So it means that we have an absorption intensity that is 2-3 orders of magnitude lower than the highest one, which is from the ground state to the first excited state. So it will be a very weak absorption, but it's possible. And we can see in the green is the same thing for the transitions starting in the first excited state. However, the structures that we have produced, they are doped so that only the ground state is doped. So since we don't have electrons in the first excited state, we will not be able to observe this absorption. Okay? So we have made the calculations and then grown a sample like this, I will show in a minute. And we made calculations exactly similar, exactly everything that I said before applies to this figure. It's just another one with different dimensions. So the central quantum well here is 8 nanometers, and the lateral superlattices, both the quantum well and the barrier, they are all 2 nanometers thick. So then we have grown these structures, and then the idea is we have 10 quantum wells on one side, the periodic structure, 10 quantum wells on the other side, and the central quantum well in the middle. And this structure is repeated 20 times, and between each of these periods, we put 300 nanometers indium aluminum arsenide, and this is to avoid exactly that we have transports through these mini band states. I can go back here just to we can have like these mini bands, they can extend from one period to the other. So we want to avoid that there's transports through this, that we lose carriers being promoted to this energy. What we are interested in is the one that is beyond the bandoffset, the one that is around 600 millielectron volts. So they were grown by MOVPE, metallogenic vapor phase epitaxy. And the doping, as I said, was such that only the ground state was doped. So here, then once grown, the samples, they were measured in the waveguide geometry. So what we did, as I said, light that is incident perpendicular is not absorbed. So we made a bevel, 45 degrees, so that the light is incident in this bevel. And then we can observe. So this is the absorption that we have detected for these samples. So we can see that we have a strong absorption at 6.6 microns attributed to the transition between the ground state and the first excited state. Even though we see this absorption, we don't expect to see a current being generated. Why? Because this first excited state is very deep. It's localized below the continuum. So one cannot extract the carrier. So, I mean, there is absorption, but the carrier will go back to the ground state because there's no way I can generate a current. I can extract. I would need another photon to extract this electron from this first excited state. And we have the absorption in this other shorter wavelengths range. And then we can see an absorption weak, but we can see, as I said, I mean, it should be 2-3 orders of magnitude lower intensity than the absorption to the first excited state. And in fact, we see a low, but we see some absorption at 2.1 micron, meaning we reach this forbidden gap. However, just absorption is not enough. If we want to make a photodetector, we need a photocurrent. So we need to measure a current on this device. And this is what we did. We measured the photocurrent for the two devices that we have grown with slightly different dimensions. And on the left, you can see that we have an absorption at 587 millielectron volts, corresponding to the absorption we just saw, around 2 microns. And this is exactly attributed to what we had predicted to be 618 millielectron volts, the transition from the ground state to the third excited state. And we see another current around 4 microns, which is attributed to the transition between the ground state and this mini band state. So we can see a photocurrent. So this means that even though we have separated this period by 300 nanometer barrier layer, it was not enough. I mean, there's still some transport, some current being carried by the electrons that are promoted from the ground state to this mini band state here. And we see that around 200 millielectron volts around here, we don't see anything which we did not expect to see, which is the transition between the ground state and the first excited state. So with this, we prove that we can, in fact, with a photodetector, reach the forbidden gap. And this on the side here is another structure, the second structure we grew, that we can also go beyond the band offset. The calculation below the one that is to the right, what we have done, since we predicted before we grew the samples that the energy would be, the absorbed energy would be 618 millielectron volts. And in fact, we observed 587 millielectron volts. We have optimized made a fit of our results. And in fact, by changing slightly the dimensions of the central quantum well and the barriers, I mean, instead of 7 nanometers, 7.1 nanometers, the central quantum well, the barriers, instead of 3 nanometers, 3.2 nanometers, and the lateral quantum wells, instead of 1.5, 1.8, then we reach 578 millielectron volts with an excellent agreement with our experiment. And I mean, these differences in thickness, this is well within the error of the technique that produces these layers. So with this, we were very happy. So even though, I mean, we have in fact reached this forbidden gap, however, we know that this signal is very low. And it would be nice if we could increase this signal. And in order to one path that we could follow to, in fact, increase this the detectivity, the responsivity of these devices, is we can explore what we call the parity anomaly. As I said before, if we have a symmetric structure, we have even, odd parallel, we alternate. However, it has been shown already that by playing with the thickness of these different layers, it is possible to have a parity anomaly, meaning we have the ground state even, and then we have two other localized states that are both odd. And then in this case, we could have beyond the band offset, we could have a transition from the ground state to the second excited states, and this would give a stronger oscillator strength, meaning a stronger absorption, and therefore a better responsivity for the detector. So we have tried to do this. So we changed the dimensions, and then the dimensions compared here, you can see on the right side of this graph of the slide. On the right side, we have a graph where we show this parity anomaly that occurs for these dimensions. And again, we have grown these structures again by MOVPE, same type of doping, same type of structures repeating 20 times, everything more or less the same. So I will go a little bit faster here. And one thing that's important to say, just as a matter of comparison, we have made a QWIP, a regular QWIP, that would detect more or less the same energy. And then here is what we have obtained the calculations. So we have for this structure here the absorption that is shown here in red and blue. These are just assuming different widths for these Lorentzians that we use in this fitting procedure. And then we can see here now the absorption is on a linear scale. Then we see that the second peak that we observe absorption, we see that we are talking now about a factor of 3, let's say 2.5 or so, and not 2 orders or 3 orders of magnitude. So here we have hope to have a much better signal, and therefore a better responsivity for the signal. And this is what we observe experimentally. So the triangles is the experimental photocurrent that was detected for this structure, and we can see, in fact, that we are almost at 500 milli-electron volt, and now we are talking about a factor of 2 or reduction, and not a factor of 2 orders of magnitude as compared to the absorption to the first excited states. So with this, we were very happy that we have this extra tool. And then if we can compare the superlattice structure with a regular QWIP, let's say, why not use, well, if you can reach with a QWIP, why not? But we can have here is analyzing the dark current, because the dark current is directly related to the noise of the detector. We want to reduce this dark current. So as you can see in this plot here, for the reference, just a regular QWIP and the superlattice, we have the current as a function of the inverse temperature. So for lower temperatures, if we see here, the dark current of the reference of the QWIP is better than of the superlattice. And the reason is because the superlattice, as I mentioned, we have the superlattice generates these mini bands. And we saw that even though these mini bands were separated, this periodic structure was separated by 30 nanometers, still we could see some current being generated. So the dark current also follows this path. However, it is at low temperatures. If we go to high temperatures, here in the inset we have this magnified. At higher temperatures, then the superlattice has a smaller dark current. And the reason is because, in fact, what happens, let me go back to the previous slide. What happens is that, in fact, the continuum here with the fact that the first localized state is a little bit beyond let's say the trigger of the continuum, in the start of the continuum. So it means that we virtually shift the continuum a little bit higher. So this means that the thermionic emission is reduced. So at low So here at low temperatures, it's the tunneling, and the tunneling does not depend on the temperature. At higher temperatures, it is the thermionic emission that dictates the dark current. So when thermionic emission is in play, then the superlattice is a better option. Therefore, and we want these devices to operate at higher temperatures, so therefore, it is another advantage to use this LIPS, let's say superlattice infrared photodetector, as opposed to the QWIPs. So with this, I can say that we have, let's say, have been able to reach this forbidden gap, and with hopes to have devices that have figures of merit that can compete in the market. So then we go to our second challenge, which is detection at room temperature. As I said, I mean, this is the Saint Graal of the infrared photodetection. And here for that, instead of using a symmetrical structure, meaning that the structural defect is in the middle, in the center, we will use asymmetric superlattice. And what is the advantage of the asymmetric superlattice? So I have the defect, let's say the quantum well that is a little bit thicker, not in the center, but to the side. What this does is the following. I mean, these superlattices, they work as Bragg mirrors in the two sides. I mean, they reflect the wave function. So what happens here is that the localized state that I will generate, if you look here, the first excited state, it will be localized in one direction and extended in the other direction. So it means here, if you see that with this type of, here is not just the wave function, this is the modulus square, I mean the probability density. So it means that to the right, this will be a preferential direction for the electrons to flow. So if I don't need to do anything, just for the way the system is built, there is a natural direction for the electron flow. So what happens is that if I have excitation to this level, I don't need to apply a potential to generate a current. If I don't need to do anything, so it works in a photovoltaic mode, no bias applied, and a current will be generated. So if we don't apply bias, it means that we reduce the noise. And if we reduce the noise, we can reach, we should be able to reach higher temperatures, hopefully room temperature. So this was the idea. So we have grown these samples, and these samples were grown by MBE, and they were grown in Princeton within this collaboration that I mentioned at the beginning. And for the asymmetric structure, what we have obtained here is, oops, sorry, I moved too fast. Here we have in the top to the left, we have in red the absorption calculated for the structure that is shown in the graph below. And we see that there is absorption in two different wavelengths. We have absorption from the ground state to the first excited state, as shown here, and to the second excited state. This, I should say this. Remember that I talked about the parity, that we alternate, and then I talked about the parity anomaly. So the parity that alternates between even and odd, this is for symmetric structures. Here we have an asymmetric structure, so this does not apply. So here we have two odd parity here state. So this is even, odd, odd. And then we have the absorption to these two levels. So this is the calculations. So we can have two color detections because these two levels are already above the original continuum. And we can see that here is the transmission here on the bottom the figure that is on the bottom to the right, we see the transmission, meaning that we can see that there's a shift of the continuum to higher energies, which reduces the thermal emission. And here on the top, I mean, the experimental results, we see, as I said, red is the absorption. In blue is the experimental absorption that fits very well with our calculations. And the triangles in gray, this is the responsivity, meaning this is essentially the photocurrent measure. This is measured at 80 Kelvin. The photocurrent measured divided by the incident power. So this is what the responsivity is, how much current I get for the incident power. And we see that we have a responsivity. So this is at 80K, but this was not our aim. Our aim was to reach room temperature, and this is shown in the right. So in the right figure, we can see that at 300 milli-electron volts, we still have our photocurrent. So in fact, we can detect radiation at 300 milli-electron volts at room temperature. So this is very nice result. Obviously, it's a very weak signal. You can see the responsivity is quite low, of the order of tenths of a milliamp per incident watt. But it was the first time that room temperature detection was, for this type of, for QWIPs, was detected. So here I show just to some of the figures of merit, just to complete the results obtained for such structures. We have the dark current as a function of bias, and with these and for different temperatures. From these curves, these IV curves, we can determine the differential resistivity, which helps us to determine exactly the dark current involved in indirectly the noise. And then we can see for different temperatures here, as a function of the inverse temperature for different bias voltages here calculated. So for 0 volts, because we could detect this signal at room temperature only in the photovoltaic mode with no bias applied. So with no bias applied is the red curve here, which is repeated up here, and then from that we can determine an activation energy for the for the thermal emission, which is 297 milli-electron volts, which is exactly the difference in energy between the ground state and the first localized state in the continuum here. Sorry, I said something wrong. Is the difference in energy between the Fermi level, this dashed line is the Fermi level, so between the Fermi level and the excited state here. So it's very good agreement. Just confirming our attribution of the transition energies and all the current that we observe to these transitions, these optical transitions. And here, as a function of temperature, we have the responsivity. So we have a responsivity, obviously, that drops a lot with temperature, the responsivity very low at room temperature, but we can detect a signal at room temperature. And here is the detectivity. The detectivity is essentially the responsivity divided by the noise current here. And we can see that, I mean, decreases a lot, the detectivity with temperature, but we can still have a signal at room temperature. And this, we were extremely happy with this achievement. And this, I mean, at 0 bias in the photovoltaic mode, this is when we reach room temperature, but these devices can operate with bias in the photoconductive mode. And with bias, obviously, they have a better performance. And we have here with positive and negative bias, we have a slightly different behavior, because if we put a positive bias here, the electrons will flow to the right, and to the right there is only one quantum well here. So, I mean, the initial state we have it will be much narrower. We have a small contribution here. This pink is from the pink state, in blue from the blue state. I mean, we have this color code. But if we apply a negative bias, then for the electron flow then to the left, as you can see, we have many other possibilities from these states in, because we have more quantum wells. So we have more initial states, let's put that way. So we have, I mean, the pink contribution is much stronger, and then we can see a real peak here, while on the left, we could see just like a shoulder. Okay, so this is just to show that we can have a two-color detector in the photoconductive mode. But the important thing about this asymmetric structure is that we have reached, in the photovoltaic mode, room temperature operation. So here is the comparing the responsivity of this device. This is a log scale. So we can see that, in fact, when we apply a bias, the performance of the devices improves a lot. And only in the photovoltaic mode, we can reach room temperature, okay? And here is the same for the detectivity. Only at room temperature we can reach. We can only reach room temperature. Sorry, I said it wrong. Only at room temperature. At room temperature, we can only have a signal if we are in the photovoltaic mode. This is the important message. So, I mean, this is what we have done. We have published, and we are very happy with these very nice results that we have overcome the two challenges we have proposed to. And now what we are working on, so these are new results that we are working, is instead of having the same lateral quantum wells just changing the position of the center of the defect, of the structural defect, we have two different quantum wells, I mean, different periods around a central one. So around here, the central, for instance, in this structure, we have two different superlattice, one to the right and one to the left, with different periodicities. And then we can have, this is what is very interesting, we can have, for one transition, let's say from the ground state to the first excited state here in blue, the natural direction of electron flow is to the right. And transitions at the energy from the ground state up to the second excited state in red, it goes to the left. So this means that depending on the sign of the photocurrent, we can, for instance, tell apart absorption of two different gases, for instance. So we can have this dual color detected that we can tell them apart, distinguish them by the sign of the current. So this is what the project we are working on now. We have already preliminary results, as you can see here on this graph, that we have already shown that, in fact, we can have this type of result with such structures. And the other thing we are working on now, we are using a lot of artificial intelligence methods using genetic algorithms to predict which structures, I mean, which quantum well width, barrier, number of quantum wells, and so forth, that we should use to optimize an objective function that normally is what we have been using is the oscillator strength, meaning the strength of the absorption, that's what we have been using, so that we can, in fact, have a structure that can give us an optimized responsivity and detectivity. So this is our news. So, I mean, to conclude, I can say that we have, with this especially designed symmetric structure, have detection beyond the bandoffset. We can explore the parity anomaly to have better figures of merit, and we can have dual color detection. And in the case of the asymmetric superlattice, we can go even further because we can operate in the photovoltaic mode and have room temperature operation. And as I showed also in this case, dual color detection. So, so this is what I had to present to you. So here, I just, for those of you who have not been to my lab, I just show here the semiconductor lab that I'm heading. This is a photo of the lab. These are some of the, so in this lab, we have growth by MOVPE, as I mentioned, that we have grown our samples by this technique. We have optical characterization, we have transport characterization, we have a clean room where we can, in fact, fabricate the device. It's a relatively small lab, but we can make, I mean, a little bit of everything, let's say, go from the material to the device and characterize the final devices. So this is a picture of the group. As I said, that this is the work of many people that have worked together, that I show here the photo. I cannot finish without thanking all the sponsors for the financial support to the project. And I would like to thank you for your attention. And then I take the chance to show Rio de Janeiro as an advertisement for, as Ricardo Reis said at the beginning, for the chip in Rio, which will be next year in this really nice city. I show you here is the university that once you are in Rio, you should visit the Catholic University where the lab is. So this is the university. This is obvious a photo of the university before COVID. So now we don't have such a large crowd in the facility, but, and this is some other pictures of Rio de Janeiro to try to motivate you to attend the conference. So that's what I had to tell you. So I thank you once again for your attention. Thank you. And I'm open for questions.
Thank you, Patricia, for the nice talk. So now it's time for questions. I'm seeing yet no questions on the chat. Please, if you have any question, please do it as soon as possible. So I have one question, Patricia. How would be the difficulty to integrate the process to do the photodetectors together in a same CMOS chip, for example?
It's possible. In fact, the question is, I mean, if with the CMOS it is everything is silicon, you have to do in parts, but you can protect one part and then make the other and try to integrate. What has already been done is monolithic integration, but then not with silicon, with other III-Vs. For instance, you can have monolithically integrated a quantum cascade laser, for instance, and a detector, all in the micro, and use it for online liquid detections for blood, for, you know, that you can in real time have an analysis. But to integrate with silicon, this is more difficult. This would require I would say, improvements in the growth you can make, for instance, this heteroepitaxy, that you can produce 3/5 on silicon. This is something that people have been working on, but still there's some paths to go to be able, in fact, to have this integrated.
So maybe in a monolithic 3D circuit, the top layer could be the photodetectors.
It's something like that. Yeah. Exactly. In fact, because you can have the light coming from below on these devices, this is possible. I mean, this is how they work, in fact.
Okay, so still no more questions in the chat. So, well, so then I would like to thank you again, Patricia, for this very nice talk.
Thank you.
If the others that are attending or seeing the talk later, you can send your question directly to Patricia email. I'm sure she's going to be happy to answer you.
Definitely.
And so thank you very much.
Thank
to
you.
finish here, just a small clip again. And then next week, we are going to have a talk by Professor Vasilis Pavlidis from Aristotle University of Thessaloniki, Greece, about signal encoding and a milestone towards energy efficiency. And if you want to have an overview of the other talks that are already scheduled, you have all this information in this YouTube channel. So thank you again, all you that attended the talk today, and thank you again, Patricia, for the interesting presentation. And so now we have several months to prepare nice works to go to see you in Rio next year. So bye-bye.
Bye.